We're going to start off by looking at a water sensor. And the point of this is to help you understand the function of a transistor. You know that water can conduct electric current. Now, pure water can, distilled water cannot. However, the water that you will typically find in the lake and certainly the ocean can conduct electric current. So can the water coming out of your tap because it contains charge-carrying minerals. So if you have some water and you put a wire, so let's say I've got a battery here, and I put a wire here and here into the water, it will conduct electric current, which means electric current will flow through the wire, through the water, and then back to the battery. And because of this, in theory, you should be able to detect water by using the water to complete an electric circuit. However, let's say you are to take a battery and you connect it to an LED. That's a light emitting diode. That's the kind of light that's the light on your phone is a light emitting diode. So if you connect that to a battery, you're going to see it light up. Well, if you connect it without any resistance, you're going to probably see it explode. But I'll let you figure that out when you experiment online. So theoretically, supposedly, you should be able to take a battery, connect it to an LED, that's a light emitting diode, and then put that wire into the water. And then electric current should flow through the LED, through the water, back to the battery and light it up. However, if you try and do this, you're going to find that it doesn't work. And the reason why it doesn't work is you won't get enough electric current going through the water. So the solution is to use a transistor. A transistor is a semiconductor device, and this in particular is called a NPN bipolar junction transistor. So this transistor is a semiconductor device, and it has three terminals on it. They are the collector, that collects current, the emitter, it emits current, and the base. And the base controls it. The way this works is if you put a small amount of current into the base, we call that IC, a small base current, it will allow a large current to flow into the collector. And then the two will combine, so you would add them together to get the current coming out of the emitter. A small current will allow a larger current. So we can use this to solve the problem of detecting water. So if our water is here, we take a transistor, and we take our battery, and if we make a connection through the water into the base, and then we connect our LED in through the collector and then attach the emitter, and we're not connecting it there, to the battery. Now when we put these probes, the ends of these wires, into the water, a small amount of current can go into the base. That small amount of current will allow a larger amount of current to come through the transistor and therefore light the LED. Now in practice, you're going to want to use a resistor here. It could be here or there to reduce the flow of current so that the bulb does not burn. In this activity, you're going to learn about the transistor, LEDs, batteries, and resistors. So I'm going to ask you now to pause this and log into Tinkercad. Now, when you log into Tinkercad, I will have sent you a class code and then your own nickname, so you don't have to create an account. It's already set up for you. And we're not going to use their 3D designs. We're going to use circuits. And click here to create a new circuit. And then in the assignment, the first thing I've asked you to do is connect an LED to a 9-volt battery. The anode connects to the positive terminal and the cathode to the negative. So over here, I want you to find a battery. Here we go. There's a 9-volt battery. And here's an LED. Now, if you just hover over, it'll tell you which one's the anode, which one's the cathode. In practice, so hopefully if shutdown is over and you're back in class, the anode is the long leg. And you can see that here. See how that's been bent out? So you can see that that leg is longer. So the first thing I'm asking you to do is to connect the anode to the positive terminal and the cathode to the negative terminal. So this is the anode, and that red line there is the positive terminal. This is the cathode, and the black is the negative terminal. And then you're going to click here, Start Simulate. You're going to see what happens. You're going to write down your observations. And I would also like you to draw a diagram. So draw the diagram and write out your observations of what happens when you hit Simulate. Okay, then the next thing I want you to do is to connect the LED and a 330 ohm resistor in series with the 9-volt battery. So for your second task, let's erase these wires. So what I'm doing, I'm left clicking on them and then pressing delete. We're going to get a resistor. Now we want the resistance to be 330 ohms. So I'm going to type here 330. Now, do you see that K? That means 1,000. I'm going to get rid of the K. So this is just 330 ohms. Did you notice the colors here changed? I'll change them back so you can see. So here, when it was brown, black, red, that was a 1K resistor. And when I change it to 330, we have orange, orange, brown. And in another video, I'll explain the color codes, and there will be a sheet where you're going to have to work your way through them. Okay, so let's reread our instructions. You're to connect an LED, a 330 ohm resistor in series with a 9-volt battery. Now, the positive end of the battery goes to the anode of the LED. And then the cathode can be connected to the resistor. Now, resistors are bidirectional. It doesn't matter which end of the resistor you attach this to. And then the other end of my resistor is going to be connected to the cathode. Is it important that we're connecting to the LED and then the resistor? And the answer is no. You could have connected to the resistor first and then the LED, and electrically that would not make any difference. People often think that it does because they imagine the charge here as being somehow more powerful than the charge here before or after a load, but that's actually not the case. Okay, so this is question 2, and then you're to click Simulate, see what happens, write down your observation, and draw the diagram. For question 3, you're to connect a 1 million ohm resistor in series with a 9-volt battery, draw the diagram, and write the observations. So to change this to 1 million, just click on it, change that to 1, and then come over here and change that. See, the capital M stands for mega, and that means million. So now we have a 1 million ohm resistor. And again, click Simulate, closely observe what happens, draw the diagram, and write out your observations. Okay, question 3. All of a sudden, this has gotten much more complicated looking, but it's actually not too bad. What you're looking at here is the same idea as we have here. We have a transistor, and it's connected to a couple of wires which will be dipped into water. So I'm going to help you set this up, and then if this was regular class time, you would build this and you're going to put those wires into the water. Since you're doing this from home and I can't get the stuff out to you, we're going to build it on the simulator, and then we're going to simulate water by using a 1 million ohm resistor. So we'll connect all of this, and then we'll just attach a resistor there with really high resistance, and the circuit will behave the same as it would if there was water there. Okay, so we're going to start off, let's position things in the same spot. So we'll put our battery here, and we'll put our transistor over here. Okay, so we're going to grab our battery, and let's get our transistor. And it is an NPN BJT transistor. So that's N-type, P-type, N-type doped silicon, and that stands for bipolar junction transistor. Now, don't worry too much about the details of that until you learn about other kinds of transistors, then it becomes important. Okay, notice here we have our collector, our base, and our emitter. Remember, the collector, that's this one right here, is going to be connected to the LED. So I'm going to connect my LED to the connector, and also see how there's a direction to the LED? This side here is the anode, and this side is the cathode. This is this is connected to the positive terminal, and connected to the negative one. Okay, so the cathode is going to be connected to the collector, and the anode is going to be connected to the positive end of the battery through a 330 ohm resistor. So I'm going to take a 330 ohm resistor, connect the anode. Let's change that to 330. And that's not kilo ohms, that is ohms. And then I'm going to connect that to the positive end of the battery. I suspect that missed. I'm not sure why that changed color. Oh. So that's connected to the positive end of the battery. So we've made the connection from here to here. Well, all the way to here, actually, to the transistor. Now, the emitter of the transistor is going to go to the negative end of the battery. So here's my emitter. It's labeled with an E. And I'm going to connect that to the negative end of the battery. Now, the base is connected to a resistor and then to the water probe. The other end of the water probe, and again, the water probe would just be 2 wires that you stick into the water. The other end is also connected to a resistor. It's a 1 kilo ohm resistor, and it's connected to the positive end of the battery. Okay, so notice, this is the positive end. I'm going to change the color of it. That's the positive end of the battery, and this is the negative end of the battery. There you go. A little easier to see. I'm going to connect a 1 kilo ohm resistor to the positive end of the battery. It won't let me connect to the wire there. There we go. All right. So the 1 kilo ohm resistor is connected to the positive end of the battery. And another 1 kilo ohm resistor is going to be connected to the base of the transistor. Now these two, this wire here and another wire coming from there, would be my water probe. Now, since we don't have water, we're going to I'm just trying to get rid of that wire. So if you start drawing a wire and you want to get rid of it, it looks like you have to connect it to something else and then press delete and it'll go away. Okay, so I'm going to simulate water with 1 million ohms of resistance. So this is my pretend water. So then we can leave this blank, press simulate, and that's simulating dry conditions. Or we can connect our probes to the resistor that's our imagined water and then press simulate to see what happens. So once you've got this built, you are to press simulate, see what happens, and then answer these questions here. So the questions are, draw out a diagram and make a speech bubble explaining the role of each component. Ask for help if you need it. So I want you to draw out this diagram. And make a speech bubble attached to each component, explain their roles. The LED lights up when current goes through it. The transistor amplifies current. So a small amount of current going into the base allows a large amount of current to run this way through the collector. This resistor keeps that LED from blowing up. It controls the amount of current in this LED. These resistors here control the current going into the base of the transistor so it never gets too high. Obviously, the battery powers everything, and the water probe detects water. So that gets inserted into where you think there may be water, and then that light should light up. The LED should light up to indicate if it's there. Okay, so I hope you got all of that. You're going to draw it out to a speech bubble. Just ask me if you're stuck on that at all. Okay. Question 5. Find the power dissipation for each resistor and the LED when it detects water. Okay, so what does that mean? You find power by multiplying current by voltage. Voltage tells you how many joules per coulomb of charge there is, and current is a measure of the rate with which the charge is moving. So if you multiply those together, you get joules per second, which is the speed at which energy is being absorbed or used by the load. And the rate at which energy is being used is power. Okay, so what you need to be able to do is measure the current and the voltage at each of these resistors. The way you do that is you get your multimeter. So we have a multimeter here. And let's say I want to measure the voltage across this resistor. It won't let me move it. Okay, so I have my multimeter here, and I'll put the negative end on the negative terminal, the positive end on the positive terminal, and I have it set to voltage. And then when I run the simulator, it's going to tell me the voltage across here. That's how I measure voltage. When you go to measure current, it's a slightly different story, so please pay attention closely. In order to measure current, you must break the circuit. So we break the circuit, and then we fix the break using the meter. So I'm going to go positive here, negative here. So now the electric current will run through the meter and then back through the load. So you click here and change it to amperage. So our multimeter is now measuring current, not voltage. So just like that, I'm going to ask you to measure the voltage and the current for each resistor and the LED when it's detecting water. So when all this is hooked up, measure the voltage here, 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 and here, and also measure the current. Remember, you get the voltage by putting the meter across it, and the current by breaking the circuit and reconnecting it in series. Find the current gain of the transistor. So what I'm asking for here is you will have more current going into the collector than goes into the base. I want you to determine exactly how much. This current here is the current going into the collector. You see, whatever current is here also goes into here, goes into here, goes into here. So whatever you get for the current going through the LED or that resistor, it's going to be the same. That's the collector current. The current here is the base current. The fraction of this divided by that is, we call it the HFE, which is, it's basically the amplification factor of your transistor at that time. So how much collector current you're getting for every unit of base current that's going into the transistor. And then find a way to make the moisture sensor more or less sensitive. Test to prove that. Now, the various things you can do here are, well, basically, you're going to leave the circuit largely as it is. You can change the value of the resistors and see if it becomes more or less sensitive. See if that light lights up brighter or dimmer. Or see if it's capable of dealing with even higher resistance here. If it's capable of dealing with higher resistance here, then that makes it more sensitive. If you're doing well and you would like to learn a bit further, you can Google Darlington pair. Which is an interesting configuration you can make using two bipolar junction transistors. So if you use two of these transistors together, you look that up. I'll let you do the research to figure out how to put them together. Then you can also make this thing more sensitive. So it's a little trick to give you a more sensitive transistor. And then finally, the last question, design a better water probe you would use in a real life situation. So I just want you to draw a diagram and write some notes about how instead of a couple of wires, how you would actually build a product that would take this circuit and use it to do something useful somewhere that you would need to detect water. Okay, best of luck, and just message me if you have any questions.